Welcome everybody. Here we have Professor Arthur Hebaka from University of Heidelberg, and he's a theoretical physicist and a cosmologist. He mainly focuses on particle physics, but right now he's going to demonstrate some interesting concepts, and we start with the gravitational waves. So you have a very interesting experiment.
Well, actually, this is a very simple model that is meant simply to show how gravity, not yet gravitational waves, but just how gravity works. Mm-hmm. And in fact, gravity works by objects, massive objects, disturbing space-time, basically curving the space-time that surrounds us. Mm-hmm. And so here's the model. This is a piece of fabric, a piece of elastic material, mm-hmm. stretched, and this should be a model, or this represents our space-time. And let's put this little marble on that space or space-time, and it just sits somewhere. And let's now put a bigger ball somewhere near it. And you see what happens is that it looked as if the big ball attracted the small one. But actually that was not gravitational attraction which exists between these objects. That would be far too weak. In fact, what happened is that this big ball curved, deformed the space-time, the fabric, and led to the small ball rolling all the way toward it. Mm-hmm. And this is how gravity works. And now, since gravity works like this, gravity is really the deformation of space-time caused by one body affecting another body. Since this is the case, there are also gravity waves, because of gravitational waves, because this surface, our space-time, is elastic, and it leads to any perturbation that I induce here, making a perturbation here. So you see, you can really see the wave traveling along this elastic material. Mm-hmm. And so you can imagine that if you have two black holes circling each other here, then there will be a disturbance of space-time over here, where our laboratory is. And so this is a gravitational wave signal that is perceived. There are tiny ripples in the elastic, if you wish, space-time surrounding us, and propagating to us from very distant parts of the universe.
So how they were detected here?
They are detected by very precisely measuring the distance between two mirrors. If this gravitational wave passes through, the distance fluctuates, changes by a very small amount, but yet this small amount can be detected. And really you should think of space-time itself being deformed, and therefore the distance between the two mirrors changing. So
using the two mirrors, they were able to detect the tiny change, huh?
They would be able to detect a tiny change in the distance between two mirrors, and thereby knowing that there was a wave in space-time, a wave of the space-time itself traveling toward us.
Mm-hmm. Okay, so why is this important, anyways?
Well, first of all, it is an important proof of concept, demonstration that the gravitational waves are really there and that we can pick them up. Mm-hmm. That is a beautiful confirmation of Einstein's theory of general relativity, and it is a very important fundamental thing. It proves to us that there were these two black holes circling each other and eventually merging, and that is very beautiful in itself. But even more importantly, at least for me as a fundamental physicist, as somebody who is interested in kind of new laws of nature and totally new physics, is that this is a new probe, a new way to test what happens in very distant parts of the universe, or what happened very early in the universe.
Such as?
Such as, for example, very early on, when inflation, towards which we will come later on, ended, or when the Big Bang occurred, if you wish. If the universe was very hot, there could be phase transitions, bubbles, there could be very violent events, to which we will come in a moment. And these events could also produce gravity waves. Maybe, probably much weaker in strength than the ones detected now, but eventually we hope that some of them that they are there, and some of them may be measured, and we will have insights into time scales very early on in the history of the universe that we cannot access in any other way.